Let's try to solve this problem here. So it mentions that the figure shows a coin on the turntable that is rotating at 1 revolution per second. So you have a coin, this is the turntable, you place a coin on the turntable, and this turntable over here is rotating at 1 revolution per second. So 1 revolution per second, in our way of writing it, it's 1 RPS, rotation per second. And you know that when you do your calculation later, you have to change it to radian per second because that's what we usually substitute in for our equation in omega. Okay, the coefficient of static friction between the coin and the turntable is 0.50. So that will be coefficient of static friction mu s, and that is 0.50. Okay, now they say calculate the maximum distance of the coin from the center O of the turntable for it to move in a circle. So when the turntable is rotating, this coin here will be undergoing a circular motion. And if this turntable is rotating with a constant speed, then this coin here will be undergoing uniform circular motion around this center axis O over here. And they ask what is the maximum distance of the coin from the center O for the coin to move in a circle. So you should be able to imagine that the coin will be traveling in a uniform circular motion, and they ask what is the maximum distance R over here. Okay, so let's try to sketch a free body diagram as usual. Okay, let me write down the 5 steps first. The first step will be to sketch a free body diagram. Then after that, to resolve the free body diagram. Once you have already resolved it, you look at the x and y axis. Okay, you look at the x and y axis to choose what equation to use. Whether to use the Newton's first law, sum of fx of y equals to 0, or you're going to use the second law, sum of fx of y equals to m centripetal acceleration. So once you pick your equation, then you will solve your question using the equation that you use. Okay, solve the question. Okay, it's more like a steps. I don't really have a specific keyword what are the steps, but usually you start with a free body diagram, you resolve a free body diagram, you analyze both of the axes, you pick the equation, then you solve the question. Okay, so let's try to sketch a free body diagram for this situation over here. We are going to sketch a free body diagram for the coin over here. So let's get this dot over here to represent our coin. And we have our axis. This is our x-axis, which is the horizontal plane. The y-axis, which is the vertical plane. As you can predict, there will be mass for the coin, so there will be weight for the coin. And after that, there's no strings, ropes, or cable attached to the coin, so there will be no tension. Is there any force being explicitly mentioned in the question or in the figure? I don't see anyone being explicitly mentioned pushing the turntable or anyone pushing a coin. There's no such thing, so there's no external force. Number 4, is there any contact surface for the coin? Yes, the coin is actually contacting the turntable over here. So there'll be a normal force exerted by the turntable on the coin. And the turntable needs to be pushing on the coin. So for the turntable to push on the coin, it has to be pushing upward. So that will be our normal force. Okay, and the last question is the contact surface rough or not? Well, they already mentioned that the coefficient of static friction between the coin and the turntable is 0.50. The coefficient is 0.50. So that means that the surface will be rough. So the surface will be rough. That means there will be a static friction for this case over here. Okay, why is it a static friction, not a kinetic friction? Is because the coin is not sliding. Remember, even though the coin is moving around this center axis O over here, but there is no relative motion between the coin and the turntable. The coin is not sliding into the turntable, the coin is not sliding out of the turntable, the coin is not sliding forward, it's not sliding backward. It's just moving along with the turntable. If it's moving along with the turntable, there's no sliding, therefore it's a static friction. Okay, so now to determine the direction of static friction, it's actually quite complicated, the way to determine it. And it actually depends on whether the turntable is speeding up or slowing down. The rotation, whether it's speeding up or slowing down. But for this situation here, since it's a constant angular velocity, So we can ignore the static friction moving forward in the direction along the path. Those static friction we can ignore it, okay, because we know that if an object is moving with constant velocity, if an object is moving in uniform circular motion with constant speed, we know that there will be no net force in the direction of motion. You cannot have any net force in the direction of motion. You cannot have any net force opposite the direction of motion, because that will speed up the coin or that will slow down the coin. But for this case, we know that it's a uniform circular motion with constant speed, so there will be no static friction pointing along the direction of the motion or opposite the direction of motion. Okay, this is like the front axis and the back axis. We think about it in 3D. The front axis and the back axis, there will be no static friction if the turntable is rotating with constant angular velocity. But what we have here, it's a static friction along the left-right axis. Whether the static friction will be pointing in towards the center or pointing out away from the center. But we know that this is a circular motion. For circular motion, we need a friction, and we need a net force to be pointing towards the center of the circular motion. So there's no other forces left. There's only static friction left. So you know that this static friction will have to be pointing towards the center of the circle in order for you to have a net force pointing towards the center of the circular path. So that static friction will have to be pointing towards the left. Okay, so this static friction here is pointing towards the center of the circle. So if you want to think about it like in terms of physics, like why is it pointing towards the center, not out of the center of the circle? You can think of like static friction, the direction of the friction is opposite the direction where the coin tend to slide. Okay, so probably if you think about it, let's watch this video over here maybe. Okay, okay, you can see that when the person spins the turntable, you can see that the plates have a tendency to move out from the table. If the sliding occurs, the plate will have a tendency to slide out of the turntable. Okay, it will slide out from the turntable. If the plate has a tendency to slide out of the table, but it is not sliding, means that when the speed of the turntable is too slow, the plate will not be sliding out, right? It has a tendency to slide outwards, but it's not sliding out. So the tendency to slide outward. So direction of static friction will opposite the direction where the object tend to slide. So opposite the direction tend to slide outwards, opposite will be inwards. That's why our how should I? That's why our static friction will be pointing inwards. The coin has a tendency to slide outwards, as we see in the video just now. So to oppose that direction, your static friction will have to be point towards the center of the circle. So this will be the free body diagram of the coin over here. Okay, so let's move on to the second step to resolve the free body diagram. Your normal force, your weight, and your static friction are all on the x and y axis. So there's nothing to be resolved over here. We move on to the third step, which is to check the x and y axis to determine which equation to use. Okay, so for the x-axis, we know that the x-axis is where the circular motion will be happening. It's a horizontal circular motion. That's the plane where the rotation is happening. So because there's a rotation, you know that there will be change of the direction of motion. So there will be change of velocity. Therefore, there will be acceleration. Okay, so because there will be acceleration, this is not in equilibrium. So because it's not in equilibrium, we are going to analyze it using sum of fx, which is equals to m as centripetal acceleration. So before we use the equation, make sure you label the direction of acceleration in the free body diagram. So the direction of acceleration will be pointing towards the center of the circle. Okay, pointing towards the center of the circle. This is the direction of centripetal acceleration. Okay, for the y-axis, we know that the coin is not leaving the turntable, it's not getting into the turntable, it's staying flat, horizontal on the table, not going up, not going down. So that means in the y-axis, the coin is at rest. Because at y-axis, the coin is at rest, we can say that at y-axis, it is in equilibrium. in equilibrium. So we are going to analyze the y-axis using sum of Fy equals to 0. All these are based on Newton's first law and second law that we discussed in dynamics of linear motion. Okay, once we pick our equation already, we can move on to solve the question by using the equation that we pick. So let's do sum of Fx equals to m centripetal acceleration. Okay, the only force that is in the direction of acceleration will be the static friction, and there's no forces pointing opposite the direction of acceleration. So the only force we have is Fs. This Fs over here, we can open it up to be equals to let's look at the situation. We are given with the rotating at 1 revolution per second, and that is just omega. Because we have omega, let's probably transform this centripetal acceleration to something that has omega inside it. So it will be mr omega square. Okay, so this is how we're going to open it up. And because they provide us not the static friction, but they provide us with the coefficient of static friction, we open it up to become mu s and m r omega square. Omega should be inside. Sorry, this is a mistake. Okay, r omega square. Okay, so this will be mr omega square. Okay, I'm not going to do any substitution yet. I have the value for mu s is 0.5, but I don't have the value for normal. Okay, most probably the normal can be found in the analysis of our y-axis. Our mass, we have the mass. We are asking for the maximum distance, and we have the omega. So right now, what do we need to do right now is to get the normal. So to get the normal, let's analyze in the y-axis. Sum of Fy is equal to 0. You can take the forces at any side to minus the force at another side. So I can take normal minus the weight of the coin. So this one will be normal equals to mg. Mg, mass of the coin, times the acceleration due to gravity. So now we know this already. We can bring in mg to replace our normal. And we can cancel out the m. And right now, if you want to get r, then that will be mu s divided by omega square. Okay, so let's figure out what is omega in terms of radian per second first. Omega right now is 1 revolution per second, 1 rps. So if we want to convert it, this is 1 revolution per second. You want to eliminate the revolution, and you want to bring in radian instead. So 1 revolution is equals to 2 radian. So that means this is 2 pi radian per second. So you can substitute in your 0.50 over here. Then your omega should be 2 pi square. Okay, am I missing out something? Yes, there's a g over here. It's mu s g. Okay, mu s g divided by omega square. So there's a g over here, 9.81. Okay, so if you calculate, put into your calculator, I believe you should get a minimum distance of 0.124 meter. Okay, so that's how you obtain the maximum distance of the coin from the center O. That means by if your radius over here is less than 0.124, your coin are able to move in the circular motion. Okay, but if your radius is greater than 0.124, what happens is the static friction cannot provide. The static friction will achieve its maximum, but is still not sufficient to keep up with the acceleration over here. You need this acceleration because this acceleration is decided by the omega already. Okay, your omega already decide what will be our centripetal acceleration. But if your static friction is not able to provide the amount of centripetal acceleration, what happens is it will break contact with the turntable, then it becomes sliding. Then you will see the situation like the plate sliding out from the turntable just now. Okay, to re-explain it again, how should I explain it? Your turntable here is rotating at omega equals to 1 rotation per second. So no matter what, if you want to not slide, if the coin does not want to slide, it has to keep up with the omega of 1 rotation per second. Okay, one circular motion, one revolution per second. The coin will have to keep up with the turntable. So to keep up with the turntable, the static friction will have to provide the enough amount of centripetal force in order to keep up with this centripetal acceleration. But we know that static friction has a limit. Okay, then because you go beyond the maximum distance, the static friction is not able to provide enough centripetal force to have that centripetal acceleration. And when that's the case, it exceeds the maximum static friction already, it drops to become the kinetic friction, and at that point onwards, your coin will start to slide, and the coin will behave like the plates in the video that we see earlier. It will slide out from the turntable. Okay, so B, the coin is placed at a distance of 5 cm from O. So 5 cm is definitely less than 0.124. That is then around 12 cm already. So coin is placed at a distance of 5 cm. You know it will continue to move in a circular motion. And now they say the speed of the rotation of the turntable is increased. So right now it is not fixed at 1 revolution per second. Instead, the speed of the rotation of the turntable will continue to increase. And they ask, what is the speed of rotation of turntable in revolution per second when the coin starts to move relative to the turntable? So right now you slowly increase from at rest, you slowly slowly you spin faster and faster and faster and faster, and they ask at which speed onwards the coin cannot remain on the turntable, instead it will slide along the turntable, probably slide out from the turntable. So to solve this question, I'll need a new page to do my calculation. So please wait for a while. So everything that we have did just now is still the same, but what has changed right now is that the omega is no longer one revolution per second. It is now slowly increasing, and at a certain value, the coin will start to slide, and we are asked to find what is that speed of rotation. Okay, the free body diagram remains the same. You still have your weight of the coin, the normal force exerted by the turntable on the coin, and the static friction pointing towards the center of the circle. If you analyze the x and y axis, the x is still not in equilibrium because there's still uniform circular motion. The y is in equilibrium because the coin is not moving up or down. It is at rest in the y axis. So let's analyze the situation again. But right now we don't have our omega. Our omega is slowly increasing, and we are asked to find what is the omega needed for the coin to slide. Okay, so sum of fx still equals to MAC, the centripetal acceleration. And for this situation, it's still Fs is equals to M. And again, we still need the speed of rotation, so we'll change it to R omega square as well, because we want omega. Then right now we know that this is mu s multiplied by n. This is mr omega square. The steps are still the same. Again, we want to find something to replace the normal over here. So we analyze the y-axis, and we find out that n minus the weight of the coin will be equal to 0. So the normal can be replaced by mass of the coin multiplied by the acceleration due to gravity. Again, we bring in the mg to replace the normal. So right now we can cross out the mass, and now our question will be asking for omega. So omega square will be equals to mu s multiplied by the acceleration due to gravity divided by the radius. Okay, and right now the radius is fixed already. They fixed at a distance of 5 cm, and they ask for the omega. Okay, so this time omega will be equals to square root of mu s multiplied by g divided by r. Okay, so once we are clear with that, we can put in our substitution. 0.50 multiplied by 9.81 divided by the radius of the circular motion, which is equals to 5 cm, 0.050. Okay, convert it to meter. Okay, so if you key in into your calculator, I believe you'll get an answer of 9.90 radian per second. Okay, so what does this answer mean is that if your turntable starts to rotate slowly, then gradually speed up, when it's gradually speed up, the coin will still continue to move along with the turntable. So if the turntable is moving slowly, the coin will undergo circular motion slowly. Then as the turntable speed up, the coin will also undergo a faster and faster circular motion until a certain point which is when the omega equals to 9.90 radian per second. Once it rotates at that angular speed, the static friction cannot provide the force sufficient to continue that centripetal acceleration. So at that point onwards, the sliding will start to occur, then the coin will slide out from the turntable. Okay, so this is the maximum speed of the rotation allowed for the coin to stay on the turntable. And I think that wraps up our discussion for this question.